Welcome everyone to our DAMSI seminar. Today's speaker is Damian Krupiewski, and he will tell us about STV. STV stands for Strategic Verifier, to my knowledge, towards practical verification of strategic ability. So, Damian, please, the floor is yours.
Thank you for the introduction. Yes, hello everyone. As already said, I will tell you about our, let's just say, experimental tool called STV. So maybe I will just start with some basic introduction to the topic, so everyone can fully understand.
Ja nie widzę żadnych slajdów. Coś jest nie tak. Czy inni widzą? Przepraszam.
Slajd tytułowy ja widzę.
Mnie też nie widzą.
Ja też nie widzę.
Znaczy ja widzę tylko Damian Krupiewski, ten użytkownik rozpoczął udostępnianie ekranu i tyle jest.
Rozpoczął, ale nie zakończył.
Wyświetla i tam obok siebie galeria, tam prelegent może jest wybrany zamiast galeria. O, jeszcze raz widzę, że okej.
O, ja miałem, a zniknęło. Coś się dzieje dziwnego.
Chyba Damian jeszcze raz włącza udostępnianie. O, jest.
O, teraz już jest okej, dobra.
To jak nie ma sprzeciwu, to chyba możemy kontynuować. Nie wiem, czy coś mówisz, Damianie, bo teraz Damian cię nie słychać.
Yes, so can you see the outline slide now?
Yes, it's visible.
Okay, so let's continue. So I will briefly introduce you to the problem that we are trying to solve and the basic theory behind that problem. And then I will talk a bit about our tool and what capabilities does it have. And then I will briefly explain implemented model checking algorithm and reduction methods. So let's start with theoretical background. So we work with ATL, that stands for alternating time temporal logic. And basically, it's one game theory meets temporal logic. So we think about agents and their interaction between them, and perhaps some coalitions, agents working together in order to achieve some goal. So as you can see here, we can create a formula that says that coalition A has a collective strategy to enforce some property. That means that when these agents work together, they can enforce this property to be true, independent on what the other agents in this scenario in the model do. And we can, the temporality here is lies with these in these temporal operators. So we can think about just next step. So what happens immediately after one transition, one action, or sometime in the future, and always in the future, which we mostly use for safety propositions and strong until. Okay, but let me just show you a simple example how this works. I will get back to the semantics variant a bit later, but let's start with an example. So let's say that we have some agents called Sherlock Holmes, and we want to say that he can solve a case without a false accusation, right? So sometime in the future, it will be true that the case is solved and no false accusations has been made. And this is a singleton coalition, and this is how we formulate some property then that we want to hold in the model. Of course, we can also have coalitions, as mentioned before. So we can say that Sherlock Holmes can work with Dr. Watson, and they are both able to save Great Britain from the crisis until the end of the story. So this is where we can use until operator. So it says that for some time, the crisis will be avoided. So the crisis proposition is false in the model until the end of a story proposition is set to true. So these are simple examples. And another example, maybe more detailed one, is called robots and courage. So let's imagine a simple scenario in which we have one carriage and two robots. These robots are numbered 1 and 2, as you can see on the slide, blue and green, and they are pushing the carriage from both sides. And the only actions that these robots have is either to wait or to push. So each robot can push the carriage forward from his perspective and wait. And if both robots pushes the carriage at the same time, the carriage stays in the same place. If one of them push and the other waits, the carriage moves to another direction, another position, and we specify only 3 positions numbered from 0. And based on this scenario, we can create a model in our logic, and this model can be seen on the right side. As you can see, we have 3 states, Q0, Q1, and Q2, and this corresponds to the different positions of the carriage on the picture on the left. And these arrows, over these arrows, we have actions. So these arrows depict transitions in the model. And these each transition have 2 actions corresponding to actions of both agents. So the first one is the action of the first robot, and the second is the action for the second robot. So for example, if we are in the state Q0, so we begin in state Q0 in the post-0 position, then let's say the first agent pushes the carriage and the second just waits, then we will get in the Q1 position because this is the transition labeled with these 2 actions that goes from Q0 to Q1. Okay. And based on this model, so first we have some scenario, then we create model based on this scenario. And now when we have this model with states, with actions, transitions, with agents, the interaction between these agents, we can formulate some properties that we want this model to have. So for example, let's say that we want to check whether the first agent, when starting from the first 0 position, so from the Q0 state, whether he has a strategy to enforce that sometime in the future, eventually, the carriage will be in the position 1. So the model will reach the state in which position one property is true. So in this scenario, just Q1 state. And if we look at the model, there are some actions that can that can be chosen by the first agent in order to get from Q0 to Q1. So, for example, as I mentioned before, the push action. But as you can see, these actions, these transitions actually depends on the action of the second robot, second agent. So if our first agent in Q0 selects action push, the second agent can either select wait, and then we will get to Q1 what we want, but he can also select push action, and then we will stay in the state Q0. Similarly, if we select the action wait for the first agent, you can either stay in the same state or we can move to the Q2 state, depending on the action of the second agent. So we do not have a strategy for the first agent that satisfies this formula, because we want to have a strategy that's independent of the actions of the second agent. Let's look at another formula with G operator this time. So we ask a similar question. We ask whether the first agent has a strategy to never reach the position 1 state. So let's look at that, what we can actually do. We start at the state Q0, and let's say we select some strategy. So let's say that in Q0 we select wait for the first agent, in Q2 we select push, and in Q1 we also select 1. As you can see, the underlined actions on this picture. And then what we can do in order to see whether this strategy satisfies our goal, we can look at the transitions that corresponds to this strategy that we choose for the first agent and remove all other transitions from the model, right? So we just leave these transitions which corresponds to our strategy. And we remove all others, and then we look at what remains and check whether the formula is satisfied. As you can see, there is no way from Q0 or Q2 to reach Q1. Q1 is unreachable. And this in this scenario, for this strategy, so the formula is satisfied. Of course, this is just to show you how it can be executed, or how one can understand what this strategy actually means. There's not actually a verification method that we normally use. Okay, so that was an example. And let's move to ATL with imperfect information and imperfect recall. So as I mentioned before, there are various semantics for ATL, and we focus on one of them with imperfect information, imperfect recall. That means that the agent cannot distinguish between some states, hence the imperfect information, and the agent does not remember his previous choices, his strategy so far, hence the imperfect recall. So, as I mentioned, imperfect information means that 2 states or more states can be indistinguishable from the agent point of view. So you can imagine this as a robot with broken temperature sensor, for example. maybe he can know the humidity of the air, but he cannot distinguish between two places with different temperatures. Then imperfect recall, so it actually means that the memory that we need for the strategies for our agents should be encoded within the state of the model. So the agent can only see what these properties, these variables, and that are stored in the current state in the model. It does not see the previous choices, its history of actions. And when we deal with imperfect information, imperfect recall, we need uniform strategies. So because for some states the agent cannot distinguish between them, we say that he must make the same decision in these two states, hence uniformity of strategies. So for each indistinguishable state, the agent must make the same decision in all this set of indistinguishable states. And then it's proven that the fixed point equivalences do not hold anymore in this semantics. So the other semantics is to have perfect information and maybe also perfect recall, but we'll focus on imperfect recall in both cases. But we can also have perfect information, and that was the example with these two robots that I showed you. This agent had perfect information, so no states were indistinguishable. To them, they always knew in which state they are exactly at some point of the computation. But when we deal with imperfect information, contrary to the perfect information scenario, fixed point equivalences do not hold, so we cannot use fixed point model checking algorithms anymore. So basically, the perfect information scenario with imperfect recall, it's basically relatively simple to solve, to verify, given some formula, but imperfect information with imperfect recall is much harder, and in fact is delta to be complete. And for simple formulas, like I showed you before, with only one temporal operator with no nesting of strategy operators, we say that it's just NP complete. Okay, so that's our basic problem, right? We want to verify some properties, some formulas for models with imperfect information and imperfect recall. And here is another example. A model for simple voting with coercion for one voter and one coercer with imperfect information from the coercer point of view. So in this scenario, we have one voter which first can decide what to vote for the first or second candidate. Then the voter decides whether he wants to give or not give his proof of vote to the coercer, and then he gets punished or not punished by the coercer. So in this scenario, the only action that coercer can choose is either to punish or not punish the voter. And depending on the voter actions, we have different epistemic classes, so different indistinguishability relations for the coercer agent. So as you can see, after the voter casts his vote, the coercer cannot distinguish between states Q1 and Q2, which is marked by this green dots line, because he does not know for which candidate the voter has voted. But when the voter gives the proof of his vote, then the cursor can distinguish between the states Q3 and Q6 on this picture. But if the voter decides not to give the vote, the cursor cannot still distinguish between these two scenarios, these two votes for candidate 1 or candidate 2, which is represented by states Q4 and Q5 marked with indistinguishability relation for the cursor. So indistinguishability relations are always created from the point of view of some agent. So the agent cannot observe something, cannot distinguish between some properties. So basically, it is usually the case that the agent can only see his own variables and some observable variables, perhaps from the environment or from the other agents. So in this scenario, the cursor cannot see the vote of the voter, he can only see it if the voter decides to give his vote away. And in this model, let's look at another two properties, two formulas. So the first one, we ask whether the cursor can in fact coerce the voter to vote for the first candidate. So either he punishes the voter or the voter votes for the first candidate. Of course, now we have imperfect information, so we must remember about these indistinguishability relations. And this is in fact false. When we look at the model, there is no way to coerce the voter, right? It's because the cursor, if the voter decides not to give his vote, the cursor cannot really distinguish between these two candidates. And there is also another solution for the voter, which may be not so trivial at the first look, but if you look at the state Q0 or state Q1, you can see that we have loops here, loops that actually depends on the voter action. So the voter action can just wait, and he can wait infinitely in these two states. So then the cursor cannot actually do anything. And this is one of the problems that we must deal with, either by modifying some semantics or either by modifying our models. And this, the second example with this safety property, so the voter can avoid punishment without voting for the first candidate. It is in fact true, because as I mentioned before, the voter can just wait. But actually, this is not something that we would want to verify, right? This is not the property that we are looking for. Hence, we can, for example, add to the model some finished property that will be only true at the end states. After the voting is finished, all the voters are punished or not punished. There is no more choices other than self loops to be made. And we can modify our formulas to say that when the voting is finished, then the cursor can punish the voter or make sure that the voter has voted for the first candidate. Something like that. So this was a brief introduction to our problem and to the theory behind this problem. And now I will show you our tool and some information about it. So what actually is this tool, this strategic verifier? So first of all, it's explicit state model checking. So when you think about explicit state model checking, you can imagine these models that I presented, and they are all encoded in the memory of the tool. So each state is represented as a set of variables, and we have this set of transitions. In fact, it's very similar to the graph representation, but we just need some more information about this action, transition, epistemic classes, etc. And the agents, of course. So there are also symbolic model checkers out there, which encodes the model in some way that it's usually using some BDD encoding, which actually uses less space in the memory, but usually takes more time to decode each state. So here we decided to use explicit state model checking. And STV supports user-defined input that I will explain in a minute. It also has web-based graphical interface, so actually anyone can use it. You just need to know the address. And it supports at this point, two main model checking algorithms that we have developed: fixed point approximations and depth-free strategy synthesis, that I will briefly explain in a few minutes or so. And it also supports reduction methods, so partial order reductions and assume guarantee reasoning. And we work with asynchronous semantics. So actually two different asynchronous semantics. We can have either action-oriented synchronization or data-oriented synchronization. So in asynchronous semantics, each agent, in each state actually, each agent maybe let's start. Okay, so in each state there is one action exactly that is chosen by some agent. So in each state only one agent makes a decision choosing this one action. So it was shown on this voting model because first the voter selects his action to vote for selected candidate, then to give or not give his vote, then the coercer decides whether to punish or not punish. So in each state only one agent performs some action, and we also have synchronization. As mentioned here, first is action-oriented. It means that if many agents have the same actions, so the action with the same label actually, it means that they synchronize over this action. So for example, in voting scenarios, let's say that we have some election authority which announces the end of the voting, and these all agents must synchronize over this action to move to the other step of the protocol. And we have also data-oriented synchronization, which means that agent can observe some data, usually from the other agents, and based on this observation, they can perform some synchronization actions. This is more natural asynchronous semantics, especially when you think about computations, computations. Okay, but we use these two semantics because the first one, the action-oriented synchronization, works with partial order reductions, and the second one, the data-oriented synchronization, works with assumed guarantee reasoning. That's why we use these two semantics. And the tool for now, it supports only reachability and safety formulas, so only F and G operators. And this is how the tools look like. It's the poster from the demo session. And you can see the main interface in the middle, so the web-based interface. We have these models here, the states, which are colored in this example, the transition. One can also show the labels for each state, for each action, for each transition, etc. And there are many options to choose from. So we can have reduction methods, we can also verify some properties, etc. And in order to create the model, to generate the model, and to actually to specify a scenario that we want to check and properties that we want to verify, we use our simple specification language, which is, I think, so relatively simple to understand. Actually, that was our main goal for this input. So as you can see, we can define in this input, we define each agent separately, each type of agent, each template of the agent, which is marked with this orange color. The agent, we have this, in this example, we have simple train controller scenario. So two trains that wants to go through some tunnel and controller that decides which train should go to the tunnel first. And so we describe each agent as a separate object, you can say, because each agent is actually represented as the local model in our scenarios. And when we combine these all agents, these local models, we get global model that I showed you in previous examples. So for each agent, we specify the initial state, and then the actions shared or not, private, so not shared actions, so synchronized or not synchronized actions. This is the example for the action synchronization. We can also use some template names that the tool will understand and generate the model based on these templates. So for example, this AID stands for ID of an agent. And we also specify some configuration options, propositions that we want to have in our reduction methods, the coalition for a formula, and the formula itself that we want to verify. Okay. And this is the model, also the simple voting model that I showed you before, but this time with two voters instead of one voter and one coercer, and still only two candidates. So as you can see, the model is much bigger, it's actually it cannot be shown. I cannot show you the whole model because it will be unreadable, more unreadable than it is actually now. But as you can see at the top, we have initial state, and we have local states list. So the IDs, the numbers of states for each agent. So each agent starts at his initial states number 0. And we have some propositions in this model. Then we have action transitions, interleaving of all possible actions. So in this scenario, why this model is so big, you may ask? Because we look over all possible permutations of actions. So either the first voter can cast his vote first, or maybe the second voter will cast his vote, and the first voter, or maybe the first voter, then the second voter, or maybe the first voter, and the first voter decides to give or not give his vote to the coercer, and then the second voter casts his vote, etc., etc. So there are many possible computations, and actually we are dealing with the state space explosion. So now we have only one agent more, and the model is much, much bigger. So you can imagine what happens for 3 voters. And this is an example of the voter model also generated by STV. So the local model of an agent, as you can see, it's relatively simple. The agent starts with this blue state at the top, and then he decides for which candidate to vote, then whether to give or not give his vote, and then the punishment is synchronized with the coercer. So this punish and not punish action is synchronized with the coercer. Okay. So now let me briefly go through model checking and then reduction methods. I will not go into details. If any of you are interested in that, feel free to ask after my presentation. So the first method that we've developed is approximation of verification of strategic ability. So as I mentioned, the main problem, the model checking for ATL with imperfect information, imperfect recall, is difficult. So we decided to approximate this verification by using perfect information for the upper bound and something called alternating epistemic calculus for the lower bound. So what does it mean? First, we can quickly compute formula result for the perfect information scenario, and if the agent doesn't have strategy for the perfect information, it means that there will be no strategy for imperfect information also. And for the lower bound, we use translation for this AMC, because in alternating epistemic calculus, we can use, we have fixed point equivalences, so we can use fixed point algorithms that are also quite efficient. So we verify our translated formula in alternating epistemic calculus, and if we get positive result, if the property is satisfied, that means that there is a strategy for the imperfect information scenario. Of course, there are situations in which these bounds does not match, so then we have no result. But there are some classes of models in which we know that the bounds will usually match, so we can get some approximation, we can get good results. And the next method is quite different. It's called DFS strategy synthesis. So before we used approximation, now we try to synthesize the strategy. And in fact, this does not reduce the complexity of the problem, but practically in many cases, in many models, it works quite well. So what is this about? We just start at the initial state, and then we recursively check all possible strategies. So in the first state, we can select the first action, A, and let's say that we want to verify whether the first agent, so this is a two-agent scenario, whether the first agent has a strategy to something in the future reach state with P, marked with P, so Q3 or Q4 state. So we select the first action, we check the first action A, and then we land in these two indistinguishable states, Q1 and Q2. And of course, we must select the same action in these two states. So either A or B. Let's start with the first one. We select A, but we see that while it lands us in the states Q3 and Q4, it can also lead us to the state Q5 depending on the second agent actions. So actually, this is not the strategy that satisfies our property. So we backtrack and then we select the next action. If it's available, we select B and we see that the formula is satisfied. Of course, this is just a simple example, but I hope you understand the basic idea. So this is just a recursive search. And of course, in the worst case scenario, we will check all possible strategies. But for many cases, especially for these voting models that have tree-like structure, the height of the tree is relatively small. So DFS strategy synthesis works quite efficiently. And it can find the solution for some cases in which the approximation gives us no conclusive result. Then, as I mentioned, we usually deal with state space explosion because we have many interleaving of actions or possible permutations of combination of these actions. And that means that the state space of the model grows really quickly. So we also need some effective reduction methods. And we implemented two of them. So the first one is based on partial order reductions. And it means that we want to generate the reduced model by preserving some temporal formula. So as I showed you before, we provide some properties that we want to preserve in the reduced model. So the result of the formula will be, of course, the same for the non-reduced model as for the reduced model. And we do this by looking at the independency of some actions. So for example, if we look at the voting scenarios, we can see that for some formulas, for example, for this coercion formula, it's usually the case that the order in which the voters vote is not really relevant. So we can choose just one arbitrary order. For example, now the first voter casts his vote and the second voter, and ignore all the other permutations or the combinations. So this creates our reduced model. Depending on the scenario, it can give us different reductions. Usually it can get us like something about 40% reduction for the transition number and about 20 or more for the state space. But as I said, it depends on the particular scenario and the particular formula that we want to verify. And the other method is based on assumed guarantee reasoning. So we create some assumption of the model, which basically means that we want, when we want to verify some property, we can just assume that something will happen. So for example, if we want to verify this voter scenario, maybe we can just look at the coercer and the voter, the interaction between this coercer and the voter. We just formulate a formula that says that the coercer can coerce the first voter, and we just assume that the other voters casts their votes and works as usual. So we do not really need to model them in details, which can greatly reduce the state space. And STV can also help with that, similarly to partial order reductions. In partial order reductions, the STV can automatically reduce the model, and in this assumed guarantee verification, STV can generate automatically specifications for each assumption group based on some extended specification. And just to conclude, so we have developed a tool that implements various methods, algorithms for model checking and reduction methods that we've worked on over the years. And as I mentioned, as we can see, these models are usually characterized by high computational complexity, and the verification of this strategy with imperfect information setting is delta to be complete, so it's difficult. And much of this complexity is due to the size of the model and to this exponential growth of the size of the model. And our tool addresses this challenge by implementing these reduction methods and also effective model checking algorithms. Besides that, it supports user-friendly input language and automated verification and reduction, of course, and this easy-to-use web interface. So, thank you for your attention.
Thank you for your talk, and let us start the discussion. Do anyone have the questions? So, as you know, as the talk is rather linguistic, so you know, I would expect people from the group of mathematical linguistics to ask something.
Yes, but perhaps we worked together and we also discussed these in smaller groups, so I don't know if they have any more questions.
Mm.
maybe I'll ask one. Well, I am co-author of many of that presented here, but just to not to leave time out the questions. Maybe could you maybe explain a bit more in detail how are we computing the complexity? So what are the what is the size of the input, and what does it mean that it is what from high complexity comes? So what are the ingredients which
yes.
need to be taken into
so
account?
Actually, the two ingredients. So first is the size of the model. So it's computed based on the size of the local models, and from that we compute the global model, which you can see an example here. But also the complexity comes from the size of the formula, right? So where I have some formulas. So for example, here we also measure the size of the formula. So actually number of nesting operators, number of temporal operators, so on. And so usually for our cases, the size of the formula is relatively small, but the size of the model is, as I mentioned, is relatively big because of the state space explosion. So the sizes of the local models are usually about, of course it depends, but in our experiments they have usually about, say, 10, 20 states for the local models. But when we combine them, we get like a few thousands or 100,000 or million states in the global model. And you also need to take in account the indistinguishability relation, so the size of the epistemic classes, which is also relevant to the complexity of this problem. You want to add something, Łukasz, maybe?
Yeah, just one thing that well, because it might seems quite unobvious why the complexity is so high. This is why I ask you to give some more details. And when we are trying to find the strategy, maybe on this large model, but still the model is, as I remember, the size of the model is polynomial from the point of view of the sizes of the single agents. But then we need to check it, to verify all the strategies in the
yes.
simplest attempts. We need to check all the possible choices that can be made by the agents, and then we have this exponential growth of the space that we need to check. So not only this graph that you showed, but also the graphs that are on the side. Let's say when we have the binary graphs of all the choices that can be made during the entire computation by the agents, and then we have this another important factor of this that make the computation so costly.
Yes, you're right. I should have mentioned that. So yes, as you can see on this picture, the strategy is described in such a way that for each state we assigned an action for the agent, of actions, a couple of actions for coalition. So if we want to check all possible strategies, we need to check all possible assignments, such assignments. So we basically multiply the number of actions by the number of states, but also we must take into account the epistemic classes. And for coalition, it's more complicated with epistemic classes because there are many epistemic classes. There can be many epistemic classes combined between many agents working in the same coalition. So we must be careful when we look at the distinguishability relation for a particular agent when we assign the strategy, just to have these correct strategies. But yes, the complexity comes from the number of strategies that we need to check.
Okay, so are there any other questions? Okay, so if there are no other questions, so let me thank the speaker again for interesting talk, and so the seminar is over. Maybe I would like to ask the chiefs of the groups just maybe to wait after seminar. Maybe we can arrange a new time slot for a new seminar. So thank you for your attention once more.
Thank you.
Thank you.
Goodbye.
Bye.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye bye.